Welcome to this Wood Solutions campus presentation on the embodied energy of timber and other building materials. All material production generates environmental impacts. Energy consumption is an important indicator of the environmental impacts of a building material or a construction system. This is due to the link between energy consumption, the use of fossil fuels such as coal to provide that energy, and the impact of carbon dioxide emissions from burning fossil fuels on global warming and climate change. Buildings consume energy in two major ways. First, large amounts of energy are needed to operate the building during its service life. This is known as its operational energy. Second, large amounts of energy are needed to make and install the materials used in constructing and maintaining the building. This is known as its embodied energy.
So embodied energy in a building is the energy that goes into making those materials that are in the building. The columns, the floors, the windows, all those components have embodied energy in them. Some of that might be a high level of embodied energy, such as in steel and concrete, or a low embodied energy, such as in wood. There is also the energy that is used in the day-to-day activities of the building, and that's driven down by making a very efficient building that is very energy efficient, the lighting, the heating, the cooling.
The embodied energy of a material in a building forms a significant component of its total life cycle energy consumption. Embodied energy calculations measure the total energy used to transform raw materials into ready-to-use building products. The result of the calculation is often expressed in a volume of energy, such as a megajoule, against a measure of mass or volume, such as a ton or cubic meter. The calculations can extend to include the energy used to construct the building and be expressed as megajoules per square meter. Embodied energy figures are calculated from detailed studies of material production and can include the energy required to obtain raw materials, process them and produce the building material, the energy used in transport during all stages of production and distribution, and in extended studies, the energy used to install the material in construction. Embodied energy comparisons are useful as strong correlations can exist between a material's embodied energy and environmental impacts like greenhouse gas emissions and global warming potential. This is because some production processes can be inherently resource and energy efficient, while others can be extremely inefficient. Embodied energy comparisons are also reasonably easy to understand and use in everyday decision making about construction choices and options. However, embodied energy comparisons have their limits. They don't include the significant difference between project conditions, such as its location, the actions of suppliers, and the seasonality of work. Also, they are averages and don't recognize the significant production difference that may exist between manufacturers. Then the sources of the energy embodied in the material are not identified. Two materials can have the same embodied energy, but the energy used to make one may be renewable energy with a low global warming potential, while the energy used to make the other may be oil or coal based and have much higher global warming potential. Lastly, simple material comparisons don't take into account the utility of material. For example, a cubic meter of concrete may have more or less utility than a cubic meter of timber in a particular application. Comparisons of the embodied energy of different construction types may compare utility. So embodied energy comparisons are useful indicators of a material's environmental impact, but they should only be used as a broad guide. This table shows embodied energy for major materials taken from the Australian Government's Your Home program. Materials are sorted by megajoules per cubic metre of material. This is almost the same sorting order as megajoules per tonne. The major things to note from the table are that hardwood and softwood have very low embodied energy. They also store carbon. Concrete has a relatively low embodied energy per tonne, but most of the mass of concrete is sand or crushed rock. The active ingredient in concrete, cement, has a relatively high embodied energy. The other major materials, glass, steel and aluminium, have, like cement, significantly higher embodied energy than timber. This is because each of these materials is produced by transforming an ore in a high energy process. By comparison, timber is simply cut from a log and dried. This doesn't consume a lot of energy, and much of this is regularly generated by burning renewable wood waste. These differences are significant and can have an impact on a global scale. Professor Chad Oliver, director of the Global Institute of Sustainable Forestry at Yale University, writing in the Journal of Sustainable Forestry, noted that swapping steel, concrete, or brick for wood and specially engineered wood equivalents would drastically cut global carbon dioxide emissions, fossil fuel consumption, and represent a renewable resource. Managed properly, this can be done without loss of biodiversity or carbon storage capacity. In summary, energy consumption is an important indicator of a building's materials or construction system's environmental impacts. Embodied energy calculations measure the energy used to transform raw material into ready-to-use building products. Strong correlations can exist between a material's embodied energy and its environmental impacts. Embodied energy comparisons are useful indicators of a material's environmental impact, but only as a broad guide. Hardwood and softwood have very low embodied energy. They also store carbon. Other major materials such as cement, glass, steel and aluminium have significantly higher embodied energy than timber and wood products. And these differences in embodied energy can have a significant impact on a global scale.